Hello, everyone. My name is Mohammad Beheshtian, and I'm going to talk about our recent paper, Software Batch Testing to Save Build Test Resources and to Reduce Feedback Time. I have worked on this project with Amir Hussein Bavand and Dr. Peter Rigby from Concordia University, Montreal. Our main goal here is to optimize testing. So, with the recent development in CI/CD pipelines, each single change is going to be tested on the pipeline. This is good because you can have feedback right away and you can prevent any failure early in the pipeline. But the problem is for large projects with many developers, this requires a lot of resources. And sometimes this is not feasible when the size of company is large. One solution for this problem is batching, which is grouping changes together to reduce the cost. And we experimented several approaches in this project to find the optimal batch size. And also, we compared them based on how much we can save using each. Currently, most of the common CI/CD tools test each change individually, which means whenever developers pushed their changes, those changes started to be tested immediately. This is actually very common and also simple, and you can have the feedback after each build. But when there are lots of builds, there would be a queue and probably some waiting time. So the formula here is that when we have n concurrent builds, we need n execution to test each of those individually. In this project, we define batch as a group of submitted changes. So this submitted change can contain one or more commits, and we call this build. So the batching, when there is no failure, we can have only one execution. But software projects always have failure, and batching can actually cause more execution than test all. We can do bisection, which is basically a binary search algorithm to improve batching. This figure shows the bisection process. So we have one failure and then we're going to split. Then we do split again and continue until we can isolate the culprit. And you can see that in total, we need 7 execution. But in this figure, another example, we have 2 failure. And when we do bisection, the second half will pass, the first half fail. Then we have to bisect again. And then build number 1, 2, 3, and 4 needs to be tested individually. And in total, we need 9 execution, which is worse than just not do batching. So for batch bisect, if all builds are passed, then we only need 1 execution. That's the ideal case. But when there are failures, it depends on number of failures. The minimum here is when there is only 1 failure, and the result would be finding a single item in a binary tree. But The worst case here is when all the builds in a batch fail. In this case, which is the maximum, would be the iteration over a full binary tree. We introduce a no batching approach, which always uses batch size 4. So in this example, we have 8 builds. Instead of running the test at first, we just group each 4 builds together. So the first batch fail, and the second batch pass. For the first batch, instead of bisection, we just test each build individually. And as you can see, we have 2 execution at first and 4 execution for those individual builds. Together, we have 6 executions, which is better than the previous approach. Our next approach is a combination of 2 previous approaches, batch bisect and batch 4. We call this batch stop 4, and here, similar to batch bisect, we do batching, and in case of failure, we do bisection until we reach batch size of 4. After batch size of 4, instead of bisection, we test each bit individually. And this is the same example that we had for batch bisect, and we needed 9 execution for batch bisect, but here we can have 7 execution, which is better, and also it's better than test all. So having 2 failures with batch stop 4, we still can save 1 execution. We mathematically show that batch stop 4 is always better. When there is no failure, you only need 1 execution. And when there are failures, the minimum is when there is only 1 failure. It is the same as batch bisect. But the maximum is less than that. So compared to previous approaches, batch stop 4 is always better. This is a comparison of all the previous approaches plus Dorfman, the blue line. So Dorfman means batching without bisection. And our batch 4 approach is a special case of Dorfman. So as you can see, the blue line is linear. The green line is the minimum of batch bisect and batch stop 4. The red line is batch bisect maximum, and the purple line is batch stop 4 maximum. As you can see, batch stop 4 maximum is less than batch bisect maximum. And the red circle shows batch 4, and we can see that in case of failure, we always need 5 executions, 1 for the batch and 4 for each individual build. We chose 10 biggest projects on Travis Torrent dataset to compare our batching approaches. As you can see, all of the projects have improvement with smaller batch sizes. But after some point, almost all of those are plateau. And Actually, for two of the projects with more failure rate, after batch size 4, the result would become worse. So most of the improvement is achieved by batches of size 4. And that's why we introduced batch 4 as a separate approach. And we're going to show that even this simple batching approach can save execution in most of the projects. Our next work is failure prediction. We want to see if we can predict failure, and using risk models, can we save some build execution? So how this is going to work? Because knowing that a commit would fail, we can't just skip that commit. We still have to test that commit because we don't know why that change is failing. But we can group all the risky changes in small batches. In this case, we would need fewer bisection, and as a result, we can have fewer execution. A previous study by Najafi and his colleagues introduced this approach. We call it risk top N. So we have a machine learning model to predict the probability of failure for each build. And then we're going to isolate that build and test it separately and test the rest together. Then again, if it's failed, we're going to isolate the most risky build again and test the rest. So in this example, we need total of 5 execution. We also introduce a new risk approach for batching. So in this approach, we use a cumulative threshold and then dynamically create our batches based on the sum of the risks for the builds. So build number 1 has failure probability of 45%. And since it's above the threshold, we're going to isolate that and test it by itself. Then we have the second batch, build number 2 and 3, can go together because the sum of them is lower than 40%. And build number 4, again, is above 40%. We're going to isolate that. And the rest of the builds can go together because it's 35% less than 40. In total, we need 4 execution, which is better. And for calculating the risk of each build, we use the same model as the previous approach. This table shows the average improvement for all the approaches. The baseline is test all, and we compare each approach to test all to calculate the improvement. As you can see, batch stop 4 is the best one, and even batch 4, which is very simple, it doesn't need any risk model and doesn't do bisection, but it can improve 47%, which is impressive. And risk models are not better than batch stop 4, although they need machine learning models to predict failures. So we can say that using batch stop 4 is recommended. And unless there is an accurate machine learning model to predict failure, there is no justification to use risk models. One parameter that can affect batching result is failure rate. We did some experiment to see the influence of failure rate. This shows 152 projects from Travis Torrent with different failure rate, and we compare the improvements. So projects with failure rate above 60% should not use batching because it only cause overhead and will need more execution. So in that case, it's better to test each build individually. With projects that their failure rate is below 40% should always use batching, and they can see improvement. And the projects in between, um, it depends on the failure distribution. So developers may need to do more investigation to see if they can gain benefit from batching. So the first thing is if you have enough resources, you probably don't need batching because if there are idle resources, it's better to use them to run the tests. And but if you do batching, um, in these projects, we have seen up to 60% of improvements. And we recommend batch 4 because it's really simple. It doesn't need machine learning models. It doesn't need bisection. It's just simple batching with fixed batch size of 4. And as a future work, if the risk model can be more accurate, the risk batch can outperform other approaches. Thank you for your attention, and please let us know your comments.